Good afternoon, ladies and gentlemen. Welcome to BASF at K 2019. Welcome to the Sunday Fun Day here at K. As you can hear, my voice has already suffered quite a bit, so I'm happy that I have an expert here who's going to do all the talking, almost all the talking. Andreas Wüst from our simulation team. Welcome, Andreas.
Welcome, Richard.
Welcome to K.
My voice is still okay, so no
That's good.
problem.
So I'm going to let you do the talking, and we're going to talk about simulation, of course, but not so much for injection molding, but for 3D printing and what is changing with that. So maybe you could give us a little introduction about the normal process of simulation for injection molding, and then tell us about the differences.
Simulation, and as we call it, virtual engineering, has a huge tradition in BASF. So for our engineering plastic materials, we do simulation support since years. And the field of 3D printing is of course not so old, and we also started some years ago with doing also simulation for 3D printed parts. Our definition of customer support in 3D printing is basically very much aligned to the concept we also have in engineering plastics. So if the customer does a project starting with the idea, going to concept phases, and in the end he wants to know if it works or not, we try to support the customer everywhere during that project phase. And also in 3D printing we try to do that. So we start when the customer has an idea and maybe asks, can we do that in 3D printing at all? But we also can help the customer if he wants to have a part tested, or if he wants to know if the part can withstand the loads. Of course, BASF as a material, as a raw material supplier, we sell material, and we also sell testing around that. And we call that, as you can see here, virtual engineering, and this is our Ultrasim approach. For the digital part, where we support with numerical models and with digital tools, it's very important to support all three corners of that triangle. We try to also have a numerical description of our material model. We do part design, and we do design support also with CAE methods, and we also try to simulate the process of 3D printing. You will see that in a second. Ultrasim, as we call our tool, is basically it's a philosophy. It's basically in our genes nowadays to use that and to say Ultrasim to that. It's basically taking into account the process of making the part, all its influences that it has on the material behavior, and then taking that into account in a simulation of the finished part. In this case it's injection molding, but on the next slide you see that we also do that for 3D printing as well.
We now have this BASF 3D printing solutions team in BASF, basically an own affiliate company working only with 3D printing. Can you describe the cooperation between the Ultrasim team and this kind of startup within BASF?
Yeah, the 3D printing solutions, as the company is called, has about, I think now, about 80 to 100 people working, plus some people inside BASF. And they are kind of organized due to the different methods you have in 3D printing. So you have powder bed fusion, you have filament extrusion, you also have photopolymers. But the fourth business line basically is services. So it goes about helping the customers make better parts. And in this services group, the virtual engineering team, the digital team, basically the computer simulation is one very important part. And I will go in the next slides through some applications here. One thing which is still kind of underestimated is when you have 20 years of experience in using plastics, for example in injection molding, you have to learn new laws of 3D printing. What can you do by 3D printing, and how should a 3D printed part look like, and what can you do? You have much higher design freedom. We will later on also see that in another part. And this is sometimes a little bit a curse, because if you look at the part and you think you see some ribs doing in injection molding, then you should forget about those ribs, free your mind and say, okay, we do some reinforcements, but they do not have to look necessarily as if they look like ribs, for example.
So it's free your mind, but also free your model, huh?
Yeah, it's basically using the better design freedom that you have in 3D printing. When it comes to description of the material, then it's different than in injection molding. In 3D printing, for example, you have this layered scheme, additive. You may basically build that in slices. and the Z direction certainly is something weak. So we have, the engineer says, we have an anisotropic failure behavior, and this means we have to define that. And our tool that we have here, Ultrasim, does the job also in 3D printing, so we can use it directly for that. I have brought with me an example. This is what we call an elbow. You see this elbow structure has a double bend, so basically every injection molder stays away and say, I don't want to do that part. Richard has it in his hands. And the question here was, if you fix that part on one flange and have some forces on the other flange, how would the best support of the outer structure, how would that look like? Of course, everybody is thinking about ribs, but ribs, forget about ribs in 3D printing. We do use a technology called topology optimization, and then you get a reinforcement that looks basically like that. And this is a kind of organic structure, and it's a fact that this topology optimization method, which we use here, is based on a biologic approach. So it mimics in an algorithm the growth of bones and of trees, and so it makes optimum structures, as you can also see that in this part. Maybe later on you can have a look at those organic structures. Yeah, of course we wanted to know how good is our simulation, how good is the prediction. So we tested this part. You see that different force directions, different fixations here. But as I was saying, it depends on how you put your part on your 3D printing machine, because this printing direction changes, and so you can have a good part or a bad part. We took those two orientations, and then you have to decide which one is the best one. In this case, we have a crack initiation area where the part breaks, we know that. And if you look at the principal stresses, which are the main stresses in that area, you see on that direction here, we have it very much aligned to this bad print direction. So this must be the bad one, and on the other side, it must be the good one. The thing is, how good are we in simulation? How good can we predict those effects? So we did a computer simulation, very non-linear stuff, all kinds of material modeling included here. And what you see on those curves, we have the two orientations. The two orientations, they give you two different values for the force, and you see that by the colors in that the simulation can very much match and compares very well to the experiment. The thing is, the part here is exactly looking the same. It's just a decision how you put it on your machine. And if you see that effect here, which is nearly 50%, then you know that you should not lose that possibility, that design freedom that you have here.
So these would be mistakes, I understand, that couldn't happen in an injection molding process. This is only happening in a 3D model.
Yes, this is because of that layered manufacturing and this anisotropic failure behavior. Of course, what we do not know is if there is even a better orientation. And this is the good thing in simulation. If you can simulate a procedure and a process once, you can also simulate it 1,000 times. So what we are doing, we are putting what's called a numerical mathematical optimization around that, and we can then, for our customer, find out which is exactly the best position that we want to make the part in the machine. Another thing that's come also from nature is about having optimum shapes. And here we also offer service for our customers in order to improve 3D printed parts. Maybe some of you know the materials in 3D printed parts are somewhat more brittle in some areas. So you have to make sure that your surface stresses is very homogeneously distributed in every corner area. And if you look at this design, or design of such a tree branch bifurcation, then this is the optimum thing you can do. And once you have understood that, you can put that in the computer and let your part grow like a tree would grow in order to give that optimum structure.
How do you feed a tree into your data models?
Yeah, it's a tree, pressed in some equations. Yeah.
Okay. Okay.
Basically, it's a growth rule. Yeah, it says where it hurts, you must grow. That's it.
Okay. Okay.
You see that here in this example, we have the original geometry And then we have put our tree growing algorithm onto that. So we have let that part grow like a tree. And then you see the optimized geometry. There is a stress reduction, in this case, 50%. And you should not lose that. Of course, that's clear. Another thing that is important in 3D printing is you can make structures that you can never think of, could never think of before. For example, those lattice structures. You have different kind of lattices. We know those lattice structures since a long time. This is our old basotect material, which is still very much used. And this also has such a lattice structure. And you also find that in the nature everywhere, because this first citation, any material is a structure if you look at it through a sufficiently strong microscope. So if you look with a microscope to trees or to some bones of birds, for example, you also see those lattices. And the thing, what we do here is we take those lattices and we have developed a methodology where we put the shape of such a lattice, it's a very simple lattice in this case, we put that shape in our CAD system. We make a finite element simulation in order to find out how this lattice behaves. We can calculate the force deflection curve, and by changing those values, by doing optimizations, we can basically run an optimization scheme in order to find the lattice that best fits to what we want to achieve with that lattice structure. So if it's a lattice that is in kind of a protection, where you have energy protection, or where you want to dissipate energy, or if it's in a shoe sole, all those things can be covered with this technology. And we offer that together with our customers with 3D printing solutions. To sum up, I give you our definition of customer support. So basically, you come to us with your 3D printing project wherever you are. We understand from the beginning to the end. Thinking additive is very important. Get rid of injection molded experiences. Hire people that don't know about injection molding directly from the university. It's the best you can do. I gave you also some simulation example in a very brief manner here. We talked about process simulation also very briefly. We also do that to simulate that process and the thermal behavior that comes up in that process. We also offer that for our customers. I gave you an example about those lattices in 3D printing, and you are already here at our booth, so whenever you have more questions, feel free to ask now or approach us later. There is also our competency area where you can also ask the other people about 3D printing.
I think we also have some interesting 3D printed and simulated examples in the Vision Venture concept car, so in case you want to know more about that. For now, Andreas, thank you very much for that very interesting, insightful talk. You're around the whole day, so everybody's free to come up to Andreas and ask him more questions. For now, thank you very much. And this was the last live talk for today already. Thank you.
Thank you.